Interstellar travel captures our imagination. The stars are far away, much farther than anything we have reached. The closest star system, Alpha Centauri, is over 4 light-years away. That's almost 25 trillion miles. With our current technology, it would take tens of thousands of years to get there. Our fastest spacecraft, Voyager 1, travels at 38,000 miles per hour. Even at this speed, it would take over 70,000 years to reach Alpha Centauri. We need faster methods to travel such immense distances. Traditional chemical rockets are not enough. They are too slow and inefficient for interstellar journeys. This makes us look at advanced propulsion techniques. Ion drives, fusion rockets, and antimatter engines are among the most promising. They offer hope for faster and more efficient interstellar travel. Let's dive into each technology and explore its potential and challenges. Ion drives are a type of electric propulsion. They use electricity to ionize a propellant, usually xenon gas. Ionization means stripping electrons from the atoms, creating charged particles. These ions are then accelerated by electric fields to produce thrust. Ion drives produce a gentle but continuous thrust. This is different from the powerful but short bursts of chemical rockets. Over time, this gentle thrust can build up to high speeds. This makes ion drives suitable for long-duration missions. They are already used in some deep space missions, like NASA's Dawn spacecraft. One of the main advantages of ion drives is their efficiency. They use less propellant compared to chemical rockets. This means they can operate for longer periods without refueling. However, ion drives have limitations. They require a lot of electrical power to operate. In deep space, solar power becomes less effective, and nuclear reactors add complexity and risk. Ion drives work through a process called electrostatic propulsion. First, the propellant, often xenon, is injected into a chamber. Here, an electron bombardment ionizes the xenon atoms. This creates positively charged ions and free electrons. Next, these ions are directed into an acceleration grid. The electric field accelerates the ions to high speeds. As the ions exit the grid, they create thrust. The expelled ions push the spacecraft in the opposite direction, following Newton's third law of motion. The expelled ions need to be neutralized to prevent them from pulling the spacecraft back. This is done by injecting electrons into the ion beam using a cathode. Engineers constantly work on optimizing these factors to improve performance. Despite their low thrust, ion drives are highly efficient in terms of fuel consumption. Ion drives offer several advantages for space travel. Their high efficiency means they use less propellant. This reduces the spacecraft's mass and the cost of launching it. They can also operate for long periods, making them ideal for deep space missions. Ion drives have already proven their worth in missions like Dawn. Dawn used ion propulsion to visit the asteroid Vesta and the dwarf planet Ceres. The mission demonstrated the potential of ion drives for complex, long-duration missions. The continuous thrust allowed Dawn to change its orbit and visit multiple targets. However, ion drives are not without drawbacks. One major limitation is their low thrust. This means they cannot lift off from Earth's surface. They need to be launched into space using conventional rockets. Once in space, they can take weeks or months to build up speed. Another challenge is the power requirement. Despite these challenges, ion drives remain a promising technology for interstellar travel. Fusion rockets are another exciting possibility for interstellar travel. They aim to harness the power of nuclear fusion, the same process that powers the sun. Fusion releases a tremendous amount of energy. This makes it a promising candidate for propulsion. Fusion rockets would use this energy to heat and expel propellant at high speeds. This could produce much higher thrust than ion drives. The concept of fusion rockets has been around for decades. Projects like Daedalus and Orion have explored different approaches to using fusion for propulsion. One of the main advantages of fusion rockets is their high energy density. A small amount of fusion fuel can produce a lot of energy. Fusion rockets could potentially reach speeds much higher than chemical or ion rockets. However, there are significant challenges to building a working fusion rocket. Containing and controlling the fusion reaction is extremely difficult. Project Daedalus was a study conducted in the 1970s by the British Interplanetary Society. It aimed to design a spacecraft capable of reaching a nearby star. The project proposed using a fusion rocket to achieve this goal. The target was Barnard's star, about 6 light-years away. Daedalus would use pellets of deuterium and helium-3 as fuel. These pellets would be injected into a reaction chamber and ignited by electron beams. The resulting fusion reaction would produce a plasma. This plasma would be expelled through a magnetic nozzle to produce thrust. Daedalus was designed to reach a speed of 12% of the speed of light. This would allow it to reach Barnard's star in about 50 years. The spacecraft would be unmanned and carry scientific instruments to study the star and its surroundings. Despite its promise, Project Daedalus faced many challenges. The biggest was the need for large amounts of helium-3, which is rare on Earth. Project Orion was another ambitious concept for interstellar travel. It was developed in the 1950s and 1960s by a team led by physicist Freeman Dyson. Orion proposed using nuclear explosions to propel a spacecraft. This would produce much higher thrust than chemical rockets. Orion's design involved detonating small nuclear bombs behind the spacecraft. A pusher plate would absorb the blast and transfer the force to the spacecraft. This would propel the spacecraft forward. The process would be repeated to achieve high speeds. One of the main advantages of Orion was its high thrust. It could potentially reach speeds of up to 10% of the speed of light. Orion could carry large payloads and support human missions. However, Project Orion faced significant challenges and risks. The biggest was the use of nuclear explosions, which posed safety and environmental concerns. Despite these challenges, Orion remains an intriguing concept for interstellar propulsion. Antimatter engines represent one of the most powerful propulsion methods. Antimatter is the opposite of normal matter. When matter and antimatter meet, they annihilate each other. This releases a huge amount of energy, much more than chemical or nuclear reactions. An antimatter engine would use this energy to produce thrust. It could potentially achieve speeds close to the speed of light. This makes it one of the most promising methods for interstellar travel. The concept of antimatter propulsion has been explored in various studies and science fiction. One of the main advantages of antimatter engines is their high energy density. A small amount of antimatter can produce a tremendous amount of energy. This means less fuel is needed, reducing the spacecraft's mass. Antimatter engines could potentially reach other star systems in a matter of years. However, there are significant challenges to using antimatter for propulsion. Producing antimatter is extremely difficult and expensive. Antimatter propulsion is not without risks. The biggest challenge is producing enough antimatter. Currently, we can only produce tiny amounts in particle accelerators. This is far from the quantities needed for a spacecraft. The cost of producing antimatter is also prohibitively high. Storing antimatter safely is another major challenge. Antimatter must be kept isolated from normal matter. This requires advanced magnetic or electric traps. Any contact with normal matter would result in a catastrophic explosion. This makes handling and transporting antimatter extremely risky. Another challenge is the efficiency of converting antimatter energy into thrust. Current concepts involve using the energy to heat and expel a propellant. Engineers are working on more efficient methods, but it remains a significant hurdle. Despite these challenges, antimatter propulsion remains a promising concept. Each of these propulsion technologies has its own advantages and challenges. Ion drives are efficient and suitable for long-duration missions. However, their low thrust limits their use for quick maneuvers. Fusion rockets offer high thrust and energy density, but face significant technical challenges. Antimatter engines promise near light speed travel, but are currently impractical due to production and storage issues. Current research is focused on overcoming these challenges. Engineers are working on improving ion drive efficiency and power sources. Fusion rocket concepts like Daedalus and Orion are being revisited with modern technology. Antimatter research is exploring new methods of production and storage. The quest for interstellar propulsion is ongoing. Each technology offers a glimpse of what might be possible in the future. While we are not yet ready for interstellar travel, the progress in these fields is promising. Continued research and innovation will bring us closer to the stars. The dream of interstellar travel continues to inspire and drive us toward new frontiers.